Several factors influence voltage drop in a conductor. Firstly, conductor length. Secondly, conductor cross-sectional area. Thirdly, current flowing through the conductor. And fourthly, the resistivity of the conductor material. The voltage drop in a conductor is calculated using the formula voltage drop equals current times length times resistivity divided by area. Given parameters are a conductor length of 80 meters, a conductor cross-sectional area of 1.6 square millimeters, a supply voltage of 220 volts, and a load voltage of 220 volts. To calculate the current, we assume a power factor of 1, meaning no reactive load. The current flowing through the conductor is given by the formula current equals voltage divided by resistance, where resistance is the resistance of the conductor. The resistance of the conductor is determined by the formula resistance equals length times resistivity divided by area, where resistivity is the resistivity of copper, approximately 1.68 times 10 to the power of negative 8 ohm meters. Substituting the given values, we find the resistance equals 80 meters times 1.68 times 10 to the power of negative 8 ohm meters divided by 1.6 square millimeters, which equals 0.84 ohms. Therefore, the current equals 220 volts divided by 0.84 ohms, which is 262 amps. Now, calculating the voltage drop, we substitute the values of current, length, area, and resistivity into the voltage drop formula. The voltage drop equals 262 amps times 80 meters times 1.68 times 10 to the power of negative 8 ohm meters divided by 1.6 square millimeters. This gives us a voltage drop of 3.48 volts. In conclusion, the voltage drop in the conductor is 3.48 volts. This means the voltage at the other end of the conductor will be the supply voltage minus the voltage drop. Load voltage equals supply voltage minus voltage drop. Therefore, the load voltage equals 220 volts minus 3.48 volts, which calculates to be 216.52 volts. Therefore, the voltage at the other end of the conductor is slightly lower than the 220 volt coil voltage of a contactor. However, contactor coils typically have a tolerance for voltage variations, and a voltage drop of 3.48 volts should not prevent the contactor from being energized. It's important to note a few key aspects regarding voltage drop calculations and their practical implications. Firstly, the resistivity value used, 1.68 times 10 to the power of negative 8 ohm meters, is a commonly accepted value for copper at a specific temperature, usually around 20 degrees Celsius. However, resistivity changes with temperature. As the conductor heats up due to current flow, its resistivity increases, leading to a slightly higher voltage drop than calculated. Secondly, the assumption of a power factor of 1 simplifies the calculation. In reality, many loads have a power factor less than 1, indicating a reactive component to the current. A lower power factor means a higher current for the same amount of real power delivered, which results in a larger voltage drop. Thirdly, the calculated voltage drop of 3.48 volts represents the voltage drop in the conductor itself. It doesn't account for any voltage drops that might occur at connection points or within the source supplying the voltage. These additional voltage drops can further reduce the voltage available at the load. Fourthly, the statement that contactor coils have a tolerance for voltage variations is crucial. Contactor manufacturers specify an operating voltage range typically expressed as a percentage of the nominal voltage, such as plus or minus 10%. As long as the voltage at the contactor coil remains within this range, the contactor should operate reliably. However, if the voltage drops too low, the contactor may fail to pull in or may chatter, causing damage to the contacts and the coil itself. Fifthly, while a voltage drop of 3.48 volts might seem insignificant, it's important to consider the cumulative effect of voltage drops in a circuit. If there are multiple conductors or components in series, each with its own voltage drop, the total voltage drop can become substantial, potentially affecting the performance of the load. Sixthly, the National Electrical Code, or NEC, provides guidelines for voltage drop in branch circuits and feeders. While the NEC doesn't mandate a specific voltage drop limit, it recommends that voltage drop should not exceed 3% in branch circuits or 5% in feeders to ensure satisfactory performance of electrical equipment. Seventhly, in practical applications, it's always a good idea to select a conductor size that minimizes voltage drop, especially for long runs or when supplying sensitive electronic equipment. Oversizing the conductor slightly can often prevent voltage drop problems and improve the overall efficiency and reliability of the electrical system. Eighthly, there are online voltage drop calculators and software tools available that can simplify voltage drop calculations and provide more accurate results, especially for complex circuits with multiple conductors and loads. These tools often take into account factors such as conductor material, temperature, and power factor. Ninthly, when dealing with alternating current, or AC, circuits, it's important to consider impedance, which is the total opposition to current flow, including resistance and reactance. Reactance arises from inductive and capacitive effects in the circuit. Impedance calculations are more complex than simple resistance calculations, but they provide a more accurate assessment of voltage drop in AC circuits. Tenthly, regular inspection and maintenance of electrical connections are essential to prevent increased resistance and voltage drop. Loose or corroded connections can significantly increase resistance, leading to excessive voltage drop and potential overheating. Now let's delve into a more detailed exploration of the factors affecting voltage drop, the implications of exceeding acceptable voltage drop limits, and practical strategies for mitigating voltage drop in electrical installations. Firstly, let's revisit the key factors influencing voltage drop. As previously mentioned, these include conductor length, cross-sectional area, current, and resistivity. Conductor length has a direct and proportional relationship with voltage drop. The longer the conductor, the greater the voltage drop for a given current. This is because the electrons carrying the current have to travel a greater distance through the conductor's resistance. Cross-sectional area is inversely proportional to voltage drop. A larger cross-sectional area provides more space for electrons to flow, reducing the resistance and, consequently, the voltage drop. This is why thicker wires are preferred for longer runs or when carrying high currents. Current is also directly proportional to voltage drop. The higher the current flowing through a conductor, the greater the voltage drop. This is because the voltage drop is a direct consequence of the current interacting with the conductor's resistance. Resistivity is a material property that quantifies how strongly a material opposes the flow of electric current. Materials with high resistivity, such as nichrome, offer greater resistance than materials with low resistivity, such as copper or aluminum. Therefore, the higher the resistivity of the conductor material, the greater the voltage drop for a given length, area, and current. Secondly, exceeding acceptable voltage drop limits can have several adverse consequences. Firstly, reduced equipment performance. Insufficient voltage at the load can cause equipment to operate inefficiently or even malfunction. Motors may run slower, lights may dim, and electronic devices may experience errors or failures. Secondly, increased energy consumption. When equipment operates at reduced voltage, it often draws more current to compensate, leading to increased energy consumption and higher electricity bills. Thirdly, equipment overheating. Excessive voltage drop can cause equipment to overheat, as the increased current flow generates more heat within the equipment's internal components. Overheating can damage equipment and potentially create a fire hazard. Fourthly, premature equipment failure. Prolonged operation at reduced voltage can shorten the lifespan of electrical equipment, leading to premature failures and costly replacements. Fifthly, safety hazards. In extreme cases, excessive voltage drop can create safety hazards, such as electric shock or fire. For example, if a conductor overheats due to excessive current flow, it can melt the insulation and expose live wires, creating a shock hazard. Thirdly, practical strategies for mitigating voltage drop in electrical installations. Firstly, conductor size selection. Choosing the appropriate conductor size is the most effective way to minimize voltage drop. For long runs or high current applications, it's essential to select a conductor size that is large enough to keep the voltage drop within acceptable limits. Voltage drop calculators and the NEC tables can be used to determine the appropriate conductor size. Secondly, reduce circuit length. Minimizing the length of the electrical circuit can significantly reduce voltage drop. This can be achieved by locating the power source closer to the load or by using multiple shorter circuits instead of one long circuit. Thirdly, increase supply voltage. Increasing the supply voltage can reduce the current required to deliver the same amount of power, which in turn reduces voltage drop. However, increasing the supply voltage may require changes to the equipment being powered. Fourthly, use parallel conductors. Running multiple conductors in parallel can increase the overall cross-sectional area, reducing the resistance and voltage drop. Parallel conductors must be properly sized and installed to ensure equal current sharing. Fifthly, improve power factor. Improving the power factor of the load can reduce the amount of reactive current flowing through the circuit, which in turn reduces voltage drop. Power factor correction capacitors can be used to improve the power factor. Sixthly, use voltage regulators. Voltage regulators can be used to maintain a constant voltage at the load, regardless of variations in the supply voltage or load current. Voltage regulators are often used in sensitive electronic equipment to ensure stable operation. Seventhly, regular maintenance. Regular inspection and maintenance of electrical connections can prevent increased resistance and voltage drop. Loose or corroded connections should be tightened or replaced to ensure good electrical contact. Eighthly, use transformers. Transformers can be used to step up or step down the voltage to optimize the circuit for minimal voltage drop. For example, a transformer can be used to step up the voltage for a long run and then step it down again at the load. Ninthly, consider three-phase power. Three-phase power systems are more efficient than single-phase systems and can deliver more power with less voltage drop. Three-phase power is often used in industrial and commercial applications. Tenthly, use active voltage drop compensation. Active voltage drop compensation systems use electronic circuits to automatically compensate for voltage drop in the circuit. These systems are often used in critical applications where precise voltage regulation is required. Let's address some advanced considerations related to voltage drop, including the impact of harmonics, skin effect, and proximity effect, as well as the use of specialized conductors and advanced modeling techniques for accurate voltage drop prediction. Firstly, harmonics are distortions in the sinusoidal waveform of alternating current. These distortions can arise from nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can increase the current flowing through the conductor, leading to a higher voltage drop. In addition, harmonics can cause overheating of conductors and equipment, as well as interference with communication systems. To mitigate the impact of harmonics, harmonic filters can be used to reduce the harmonic content in the current. Secondly, skin effect is a phenomenon in alternating current circuits where the current tends to flow near the surface of the conductor, rather than being distributed uniformly throughout the cross-section. This effect is more pronounced at higher frequencies and with larger conductors. The skin effect effectively reduces the cross-sectional area available for current flow, increasing the resistance and voltage drop. To minimize skin effect, conductors can be constructed from multiple strands of wire, known as stranded conductors. The increased surface area of stranded conductors reduces the skin effect and improves current carrying capacity. Thirdly, proximity effect is a phenomenon where the current distribution in a conductor is affected by the presence of nearby conductors. When conductors are placed close together, the magnetic fields generated by the current in one conductor can induce currents in the adjacent conductors, altering the current distribution and increasing the resistance and voltage drop. Proximity effect is more pronounced at higher frequencies and with closely spaced conductors. To minimize proximity effect, conductors should be spaced as far apart as possible or arranged in a configuration that minimizes the interaction between their magnetic fields. Fourthly, specialized conductors are available for applications where voltage drop is a critical concern. These conductors may be made from materials with lower resistivity, such as silver or special alloys, or they may have a larger cross-sectional area than standard conductors. Specialized conductors can significantly reduce voltage drop, but they are typically more expensive than standard conductors. Fifthly, advanced modeling techniques can be used to predict voltage drop in complex electrical systems with greater accuracy. These techniques include computer simulations and finite element analysis, which can take into account the effects of harmonics, skin effect, proximity effect, and other factors that are difficult to analyze using traditional methods. Advanced modeling techniques are often used in the design of large electrical systems, such as power plants and industrial facilities. Sixthly, the impact of altitude on voltage drop should also be considered, especially in high-altitude installations. At higher altitudes, the air is less dense, which can reduce the cooling capacity of electrical equipment and increase the operating temperature of conductors. Higher operating temperatures can increase the resistivity of conductors, leading to a higher voltage drop. In addition, the reduced air density can decrease the dielectric strength of insulation, increasing the risk of insulation breakdown and electrical arcing. Seventhly, the effects of electromagnetic interference, or EMI, on voltage drop should also be considered, especially in sensitive electronic circuits. EMI can induce currents in conductors, which can alter the voltage drop and cause malfunctions in electronic equipment. To mitigate the effects of EMI, shielded conductors can be used to block electromagnetic radiation, and filters can be used to suppress unwanted currents. Eighthly, the use of smart grid technologies can also help to manage voltage drop in electrical systems. Smart grids use sensors and communication networks to monitor the voltage and current at various points in the system, allowing for real-time adjustments to be made to optimize the voltage profile and minimize voltage drop. Smart grid technologies can also be used to detect and diagnose voltage drop problems, allowing for timely repairs and maintenance. Ninthly, the impact of aging on voltage drop should also be considered. Over time, conductors and electrical connections can degrade due to corrosion, oxidation, and other factors. This degradation can increase the resistance of the circuit and lead to a higher voltage drop. Regular inspection and maintenance can help to identify and address aging-related voltage drop problems. Tenthly, the importance of proper grounding and bonding in minimizing voltage drop should be emphasized. A properly grounded and bonded electrical system provides a low impedance path for fault currents, which can help to reduce voltage drop during fault conditions and improve the overall safety and reliability of the system. Now consider the specific application scenario. The application is to supply a 220-volt contactor coil at the end of an 80-meter conductor with a cross-sectional area of 1.6 square millimeters. The primary concern is whether the voltage drop will be excessive, preventing the contactor from energizing reliably. Here are some additional factors to consider. Firstly, contactor coil characteristics. Contactor coils typically have a specified operating voltage range, which is the range of voltages within which the contactor will reliably pull in and remain energized. The operating voltage range is usually expressed as a percentage of the nominal voltage, such as 85% to 110%. Before making any decisions about conductor size or voltage drop mitigation, it's essential to determine the operating voltage range of the contactor coil. Secondly, inrush current. Contactor coils draw a significantly higher current when they are initially energized, known as the inrush current. The inrush current can be several times higher than the steady-state current. The voltage drop during the inrush current period can be much greater than the voltage drop during steady-state operation. Therefore, it's important to consider the inrush current when assessing voltage drop. Thirdly, ambient temperature. The ambient temperature can affect the resistance of the conductor and the performance of the contactor coil. At higher temperatures, the resistance of the conductor increases, leading to a higher voltage drop. In addition, the contactor coil may be less efficient at higher temperatures, requiring a higher voltage to energize. Fourthly, conductor material. While the initial calculation assumed copper as the conductor material, it's important to verify this assumption. If the conductor is made of aluminum, which has a higher resistivity than copper, the voltage drop will be greater. Fifthly, connection quality. Poor connections at the source and load can significantly increase the resistance of the circuit and lead to a higher voltage drop. Ensure that all connections are clean, tight, and properly made. Sixthly, load diversity. If there are other loads connected to the same circuit, the voltage drop can be affected by the current draw of these other loads. Consider the load diversity when assessing voltage drop. Seventhly, future expansion. If there are plans to add additional loads to the circuit in the future, it's important to consider the impact of these additional loads on voltage drop. Oversizing the conductor slightly can provide some margin for future expansion. Eighthly, the use of a step-down transformer at the load can be considered to compensate for voltage drop. A step-down transformer can be used to boost the voltage at the load, ensuring that the contactor coil receives the required voltage. Ninthly, the use of a dedicated circuit for the contactor coil can be considered to minimize the impact of other loads on the voltage drop. A dedicated circuit will ensure that the contactor coil receives a stable voltage, regardless of the current draw of other loads. Tenthly, consult with a qualified electrician. It's always recommended to consult with a qualified electrician to assess the specific application requirements and ensure that the electrical installation meets all applicable codes and standards. The electrician can perform a thorough analysis of the circuit and recommend the best course of action to mitigate voltage drop and ensure reliable operation of the contactor. By carefully considering all of these factors, it's possible to design an electrical system that provides a stable and reliable voltage to the contactor coil, ensuring its proper operation and preventing any potential problems.